Sorry, but that part of our lecture is not going to be posted to YouTube. I accidentally opened up a page that had students' grades on it. So let me get to where I was going. If you go to our Canvas page, I just posted in here under files, or no, it's been here. I'm sorry. It's this thing called Related Rate Worksheet. You can download that if you'd like. I'm going to be working off of that right now. So if you want to know where you can get one of these, that's where it is. So here it is. This is the worksheet. And what it does is it allows you to, it kind of like gives you almost like a table to fill out to do one of these problems. So we're gonna draw a picture of the scenario we're talking about for the exact moment in question. Then we're going to draw a picture of the scenario in general. So I talked to you about this last class. I have a general picture and then an instant or exact moment in time picture. We want to write down what we're given. We want to write down what we want. We want to find an equation. We want to do implicit differentiation on that. And then we want to get a solution. And then this will be for any scratch work we have. Okay, let me put the problem right here. Let me see if I can squeeze a problem in here. Get off of there. Not sure what's going to happen if I try and paste this in here. Yeah, it's going to move it down there. Come on, man. All right, it's not letting me grab this for some reason. Oh, there it is. There we go. Okay, so there's the problem. All right, y'all ready? Okay, so we are given that the area of a circle is increasing at a constant rate. We want to know how fast its radius is increasing when the area is 5 square feet. So the picture at the moment in time that we're talking about is a circle, right? It's a circle that has an area of 5 square feet. So we know this is the radius, right? Whatever R is here. We know that at the moment we're talking about in time, the area is 5 square feet. Agreed? That's what's happening at the instant in time we're talking about. So let me ask you, if the area is 5 square feet, then can we find the radius?
Yeah.
Yeah, if we know the area of a circle, then we should be able to find the radius, right?
Yes.
Yeah, we should. So radius, I'm going to put here equals. I'm going to put a check mark, meaning we should be able to find it. Okay, it's not given to us, right? You know, it's not just like explicitly given to us, but because we know the area, we know that we would be able to find the radius of the circle. So that's the exact moment in time. Now, what I'd like to do is draw a picture of the general situation, which is a circle that's growing, right? So in this problem, in this picture, my radius is R, right? And the area is, well, pi r squared, isn't it? I mean, but we don't know what the area is because we're imagining that in this picture, things are changing. So the radius is changing, that means the area is changing. Y'all okay with, understand the two different pictures? One's a snapshot, the other one is a general situation.
Yes.
Okay, now what are we given? And I said to look for certain words when we're looking at this, what we're given. We want to be looking for derivatives or speeds of things, rates of change. So it says if the area of a circle, right, if the area of a circle is increasing at a constant rate of 1/5 square feet per second, do you all agree that that is a rate, that is a speed, that is a derivative then?
Yes.
It's the rate at which what is changing?
The area.
The area. So I'm going to write dA, the rate of change of area, with respect to time, t. So t here is our time variable. This is 5 square feet. I'm sorry, not 5, 1/5 square feet every second. Okay, that's given to us, right? What do we want to know?
How
How
fast
fast?
is that 5 foot?
Okay, how fast the radius is increasing. How fast? We want to know the speed of the radius, don't we? The speed of the radius means the rate of change of the radius, which again means we are looking for a derivative. The speed of what? Radius, right? R with respect to time. We want to know that, right? That's what we want to know. And when do we want to know that? At exactly what moment?
And when the area reaches 5 feet?
When the area is 5, at exactly the moment that the area is 5 square feet. This is what we're given. This is what we want, and this is the exact moment we want it. Now, what I told you last class is that at this point in time, what you want to do is find an equation. All right, we want to find an equation that relates that variable to that variable. Any equation that you can come up with that still is consistent with the geometry of this problem, right, which is a circle, that would relate the area to the radius. And I hope it's obvious we have that equation. Area is pi r squared, right? That's the same equation we had in the previous problem. So I'm going to write the equation down here now. Area is pi r squared. Once we have this, do not plug in 5 for area. Do not do that. You want to look at the general equation, and at this point is where we do implicit differentiation. And so I'm going to take the derivative on both sides of this equation with respect to what variable?
R, right?
Time.
My bad.
Time. So we're going to do derivative on the left side with respect to time, and derivative on the right side with respect to time. If you look back at last class, this is the exact same equation we had from the last problem, and this is the exact same derivative we had from the last problem. So the left side, this right here, what is the derivative of a with respect to t? Well, I don't know. It's the derivative of a with respect to t. That's what it is. And then here, we're doing the derivative, and do we need to do product rule?
No.
Do I have to do product rule
No,
here?
no, because it's pi is a constant.
That's right. We do not need product rule because pi is a constant, which means that my answer is going to be pi. Pi comes for the ride, times, now you have to take the derivative of the r squared. And you have to be careful because you're doing it with respect to t, right? So we're taking derivative with respect to t of r squared here. Let's go ahead and do that. Pi, let's see, derivative of r squared with respect to t. Volunteers?
dr over dt.
Yes. What about the r squared though?
It's gonna be 2r.
2r. Okay, and then after the 2r,
It's
the
gonna be
dr
4 over
dt. Good. Okay, there it is. This is our master formula now. This is it. We should be able to get the solution from this. So let me just write this down. I'm going to write it in my scratch work area. This is what we've come up with. And if you look at this equation that we differentiated and we got this new equation, you'll see that what we wanted in the problem, right? What we wanted to find out, we wanted dr dt, right, is right here. What we were given in the problem, dA dt, is right here. And the only thing we don't know, right, the only thing we don't know right now is r, right? That's still a question. What is the radius of this circle at the exact moment in time? So now we have to actually go back. And remember how we said over here, we knew what it was? I mean, like we knew we could find it. We didn't know what it was. It's time to go find what the radius was. Okay, because I'm gonna be plugging numbers in here, right? dA dt, I'm gonna replace it with 1/5. I need to replace r with a number, which I'm gonna get from here, and then dr dt is what we're looking for. So we'll solve for this once we get these numbers. So I'm gonna go back to this. The area of a circle is pi r squared, we know that. And the area is said to be 5, and then pi r squared. And So to solve for r, I divide both sides by pi. And then I take the square root on both sides. So r is equal to the square root of 5 over pi. Understand that, everyone? I think we're ready to plug it all in. dA dt, I'm going to replace with 1/5 equals 2 pi times r, which we just said is the square root of 5 over pi, then dr dt. All right, now I think I'm just going to use my calculator. So the left side on my calculator is 0.2 equals, now I'm going to do this on my calculator. I'm going to do 5 divided by pi. And then I'm going to take the square root of that. So this becomes 2 pi times, that number is 1.262. I'm just going to round 3 decimal places, times dr dt. I'm going to go ahead and multiply all these together now on my calculator. I get 0.2 equals 7.9227 dr dt. And finally, I will divide both sides by 7.927. I get about 0.025 is dr dt. Now we have one last thing to do. Are there any questions on the math that I've done here? The arithmetic here.
I just wanted to know that if time is going to be in the problem, is that always going to be our independent variable?
Not on every problem, but on most of these problems, time is our independent variable. On most of them it is, but I can't say all of them. Yeah. Okay, so what we need, the last thing we need here is to figure out what the unit is for this number. Okay, so the way we're going to figure out the unit is to look at 2 key things. These 2 things right here, r and t. So r is the radius, right? And the radius is a length. How are we measuring lengths in this problem? What unit are we using?
Feet.
Feet, right? So our answer should be 0.025 feet per, now time, look at the bottom, t. Time is the measurement of time. And what is our measurement of time in this problem?
Seconds.
Seconds. All right, there we go. 0.025 feet per second. So that's saying that, this is actually, when I made this program, I actually made it so it would be exactly correct. If we let a circle grow so that the area grows at a constant rate of 1/5 square feet per second, here it is, then at the exact moment that the area was, what, 5?
Yeah, 5.
At 5, so let me go to that exact moment. Let me see if I can back it up to that exact moment where the area was 5. It's gonna be hard for me to get there. Oh, I went too far. It's right around there. I'm almost there. There's the area is 4.92. Right at that exact moment, right? So imagine this thing was growing right at that exact moment. At that instant in time, the radius, which is, the radius is this point to that point, right? That radius is growing, isn't it? At that instant in time, the radius is growing. The rate at which that radius is growing is 0.025 feet per second at that instant in time. Now, if we move to another point in time, it's going to have a different, the radius will have a different rate of growth. Okay, it's what's happening at that instant that we're interested in. Any questions? All right, let's do another one. New problem, an expanding sphere. So we're looking at a sphere, not a circle. So this is a three-dimensional object instead of a two-dimensional object. And here, I'm going to give you an example where the radius is increasing at a constant rate. So this is just like the circle, the first problem we ever did with the circle, but now we're looking at a sphere. So what happens if I start letting a sphere grow where the radius grows at a constant rate? So keep your eye on the radius here. Let's keep an eye, let me speed it up. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. So the radius is constantly growing. Look at the volume though. Is the volume constant? In the beginning, 1, 2, 3, 4, 10, 20, 100, 2. That's getting, let me slow it down. It's a little hard to see. Look at how fast the volume goes. 20, 30, 40, 50, 60, 80, 90, 100. Now 200, now 300, now 400. See how fast that volume is getting bigger? In the beginning, it's slow, but as the radius gets bigger, you add more and more volume. So even though the radius grows at a constant rate, the volume does not, right? The volume does not. So what we're going to ask is, at a specific point in time, how fast is the volume increasing? And you might be, right now, you might be asking, like, why in the world would we ever want to know something like this, right? Like how fast something is growing or changing at a certain instant in time. But this is very, very important in many applications in engineering and physics. I mean, the first thing I can think of is, if anyone here knows, I'm just trying to come up with just like a generic example. If anybody knows how an engine works, okay, you have cylinders, and then inside the cylinder, you have this, what do you call this? Well, this is
Pistons.
piston. Okay, so you have a piston in here, and then you have attached to the piston, you have a what? I know there's some car
Rod.
people in here. A rod? Is that what you said?
Yeah,
And that attaches to
the
crankshaft, which is actually the thing that spins, right? And so what happens is, as this point goes around, this piston goes up and down through the cylinder. And so what you could ask is, okay, if this thing is spinning, oh, you know what? We have the internet. Let's see if we can find animation. Piston.
4-stroke.
Yeah, let's see if we can find a quick animation of it. Here we go. You gotta watch an ad first, no? Can y'all hear this or no?
Yeah.
You can hear it.
See if there's an
So
animation.
how do they work?
Well, it's
The
not-
first
it's
step
not
in this
showing.
cycle is that this is where the spark plugs
Right.
light the gas on fire, creating
That's no good. Here we go.
Here's a different perspective on how the piston
This
drives the
is like a
crankshaft through the connecting rod.
1950s. There we go. There we go. So y'all see what's happening here?
At
Oh,
the
there's
top of the
perfect.
cylinder are the valves, which let in the gasoline and air mixture. For increased
So what we could ask in a physics setting or an engineering setting,
at the
right
top of the
there at that moment in time, right there at that moment in time, if we know how fast this is turning, which is the RPMs of the engine, that would be your revolutions per minute of the engine. At a specific point in time, I could ask right then, like right when I froze this, how fast is this piston coming down at that instant? Because it's not the same, because of the shape of everything, it's not always moving up and down at the same speed. So you might want to know when it gets to the top of the stroke, when the piston is up here, you might want to know how fast is it coming up? That would give you some idea of the compression. So I'm just trying to get you to see that there are applications to this, but we're starting out with very simple problems like a circle growing or a sphere growing. And then later on, you can make it more complicated, all right? But we got to start somewhere. I hope that gives you some insight into why we're doing this. Any questions? We're going to do this problem. Oh, hey, everyone. I sent the review out. Did you all get that?
Yes.
I sent the
Sure did.
review out. Yeah, you're welcome. Oh, no one said thank you? It's okay.
You're
Yeah.
very kind.
Much thank you for that.
Yeah. Come on. How did this work last time? All right.
Sir, quick question.
Yep.
The sheet that you're showing us that you're gonna work the problem on, is it useful for all word problems?
It's useful for most of the related rate problems. Yes. Yeah. I mean, I would say for most of what we're going to do in this class, this is sufficient.
Is she allowed on the test?
I mean, if you want to print a couple out, you can have them. That's fine. That's fine. This is really just to show you that there is a systematic approach to this. All right. There is kind of a systematic approach. But yeah, I think once you do enough of these, you don't need the sheet anymore. You just can do it, but this will at least get you started. All right. So I want to do this problem. If the radius of a sphere is increasing at a constant rate of 2 feet per second, how fast is its volume increasing when the volume is 36 pi cubic feet? Okay, so let's draw the picture at the moment in time. I have a sphere. If you've never drawn a sphere, that's one way you can do it. You draw a circle and then you just draw this weird sort of ellipse in the inside. And then you can put the center like there. And then you draw just a line from here to the edge, and that would be your radius. And at the moment in time we're talking about, all I know is that the volume must be 36 pi cubic feet. So if I know the volume is 36 pi cubic feet, will you be able to tell me what the radius is if you need to?
You should be able to
Yes.
get it right.
You
Yeah.
should be able to get it, right? So I'm going to put a little check mark here because again, I should be able to get the radius if I know the volume. Yeah. Okay, let me draw the picture at the moment. Sorry, the general picture. So here's my sphere. Now the sphere is growing, right? And so now the radius is not fixed. And that means that the volume, I can't put the 36 pi, but that means I need the volume of a sphere, right? I need the volume of a sphere. And that may be something you don't know off the top of your head. But I do provide you formulas for this class. And on the very first formula sheet, you'll see that there is a sphere on the formula sheet, and it shows that the volume, it's hard to read this, it's 4/3 pi r cubed. 4/3 pi r cubed, okay? So you would have access to that information during a test, 4/3 pi r cubed. Now, what are we given? I feel like calling on people. Let's see if I can find my roster. See, who did I call on last time? I don't think I called on Matthew Gutierrez, did I? Last time? Okay, so what am I given?
That the volume is 36 pi feet cubed.
Okay, that I am given that, but in terms of derivatives, in terms of rates of changes of things.
Okay, so then the constant rate is 2 feet per second.
Okay, and that's the rate that what's changing?
The radius.
The radius. So I'm going to write what here? D what over D what?
dr over dt.
T, okay? So R stands for the radius
Mm-hmm.
and T represents the time, right?
Yeah.
And you're telling me that that's 2 feet per second. I agree, that is given to us. Now, what do you want to know?
How fast the volume's moving.
Okay, so you want the rate of change of the volume, don't you?
Yes.
How would we write that as a derivative?
So that would be dv over dt.
dv over dt. And that I want to know, right? And when you're writing down what you want to know, you also, Matthew, you also write at the moment we're talking about. So at what moment in time?
At 36 pi feet cubed.
Yes, at 36 pi. Now, at what's 36 pi?
That's the volume.
That's the volume. So at v equals 36 pi. So if, Matthew, do you have any questions on that? I mean, you said
No.
it, you did it right.
Yeah,
but
I understand it.
everything okay?
Yeah, I'm good.
So look, I'm going to just recap. We drew a picture of the exact moment in time. We drew a picture of the general situation where we can't fix anything. We assigned variables and any rates of change. We wrote down what we were given and what we wanted to find. So what we're given and what we want to find, this all makes sense. R here is the radius. R is in our picture. V here is our volume. V is in our picture. All of our variables relate to the pictures, and the equations are all connected to one another, right? Last thing, or next thing, sorry, is find an equation which somehow relates what you are given to what you want to find. So Brian, is Brian Hernandez here? Brian, B with a B, Brian?
Yes.
So I said when you're going for the equation, you want to find an equation that relates that variable to that variable. Any equation you can come up with that relates the radius to the volume for a sphere.
Wouldn't we do? Wouldn't we do an equation that had area in it, which was equal to volume or similar to volume?
Well, I think we've done something with volume and area together, but we're not trying to relate area and volume. We're trying to relate radius and volume. Look at what we wrote down in the general picture, Brian.
Volume is equal to 4/3 of pi times r cubed.
There you go. That's an equation that relates those two variables together, right?
Yes.
For a sphere. So there it is. We can use that equation, right? So let's use it. We're going to write it down here. V equals 4/3 pi r cubed. And once we have that, we are going to differentiate it with respect to time. That's our next step. So we take the derivative with respect to time of v on the left side and the derivative with respect to time of 4/3 pi r cubed, the right side. Brian, you want to keep going?
Sure.
Okay, what's the derivative on the left side? What do you get?
Wouldn't it be just the d over v, sorry, dv over dt?
That's it. Okay, that's the left side. Equals, now, Brian, you have 4/3 pi. That's all a constant, isn't it?
Yes, you mentioned that in the last problem.
Yep. So we can just write that down, right? 4/3 pi.
Yes.
And now all you have to do is take the derivative of r cubed with respect to t. So what's the derivative of r cubed with respect to t?
3r squared.
Okay, 3r squared. Almost done. There's a little more to put on there.
Times dr over dt.
Times dr over dt. Perfect. Any questions on that?
Shouldn't there normally only be dv over dt in this, what you finished writing down?
No. No, because remember, go back. I'm going to copy this real quick. I need to move up here, put it here. Oh, maybe I'm not putting it there. Okay, here's where we are, right? What is it that we were given? We were given dr dt, weren't we?
Yes.
So this we have. We want dv over dt. That's right here. Okay, so I'm glad it's here, right? Because we want that.
Okay.
And so the only thing that we don't know right now in order to figure out what this is what radius is, right? That's the only thing I don't know. If I know this number, then I can fill this in with a number. And then this right here, drdt, that's 2. So I can fill that in with a number, and then that'll give me dvdt. So the thing at the end of this, Brian, when you get this equation differentiated, you just want to look at it and make sure that everything in here can be filled in except for the thing you're looking for. And then you'll just solve for it.
Okay.
So we still need radius, don't we, everyone? So Braxton, are you here?
I'm here.
Okay. Any idea of how we can figure out the radius?
Let's see. Let's see. We can use the v equals 4/3 pi r cubed,
Mhm.
and let's see. I think we could plug 36 pi into that.
That's right.
For
So
the
look,
v.
at this point in time, everyone, now you can be looking at the instant in time. Now you can. And we know that the volume, right? The volume is 36 pi. And so what we know is that 36 pi must be equal to the volume of a sphere, which is 4/3 pi r cubed. And now I can just go solve this for r. Right? Good, Braxton. So we're just going to do this. This algebra is actually not as bad as it looks. Divide both sides by pi, and the pi is gone. Multiply both sides by 3 and divide both sides by 4. You should get 27 for r cubed. And then take the cube root on both sides, and you should get r is 3. Everyone clear on the algebra that I did there?
Yes, sir.
Okay, so now I know what r is. So I think I'm ready to put this all together. dv dt should be 4/3 pi times 3 times the radius, which I just found was 3, squared times dr dt, which is 2. So this is 2, the radius was 3. And this is just a bunch of numbers. Look at this. These 3's cancel. And let's see, I just get 4 times pi times 9 times 2. 72 pi, which is approximately, on my calculator, 226.195 is dv/dt. The volume is changing at a rate at that instant in time, right? At that instant in time that we're talking about, the volume is changing at a rate of 226.195 what?
Feet cubed per second.
Feet cubed per second. So how are we getting that? We look at the unit here, volume, right? How do we measure the volume of something? It's the unit cubed. And our units in this problem are feet. So this will be feet cubed per our unit of time. And our unit of time in this problem is seconds. So I'll say per second. There it is. Are you starting to get an idea of how this process works? Picture what we're given, what we want at the moment we want it, equation, implicit, solve for what you're looking for. You might have to go back and plug some stuff in to like figure out some of the unknowns.
And for a test, if we get a problem like this where we have pi, do you want us to leave pi in the equation, or are we allowed to use a calculator to figure out the approximate value?
Either one. If it gets really complicated, like if you have pi under a square root or something, you can just go to a decimal. That's fine. All right, I'm going to do another one here. but I'm not going to bring up that sheet, I don't think. You see, I might. Let me see.
That sheet is really helpful though.
Good, good, good. I'll work it without the sheet, knowing that you can fill in your own sheet. Okay. All right, new problem. A plane is flying horizontally at an altitude of 2 miles and a speed of 600 miles per hour. The plane is headed directly over a ground-based radar station. At the moment the plane is 6 miles from the radar station, how fast is the distance between them changing? All right, so one assumption here in this problem, okay, and this is because we don't want to make this too complicated, is we're going to assume that the Earth is flat, okay, so that the ground is flat, even though we know in reality it's not. All right, well, some of you might believe otherwise, but most people believe the world is round, the Earth is round, curved. Okay, so here we go. I'm gonna try and draw a picture. All right. So I have on the ground a radar station. This may not be my final picture. I'm just trying to get a feel for what's going on here. I have a radar station on the ground. Then I have a plane that's flying overhead and it's flying horizontally. So the plane is flying kind of along a horizontal line like this. And the plane is flying, let's say, in this direction, okay? My plane is just going to be this dot, okay? I also know that the plane is 2 miles high. So I know that the distance from here to here is 2 miles. And that's not changing, okay? Same altitude the whole time. I also know that the plane is flying at 600 miles per hour. That's a speed, isn't it? 600 miles per hour is a speed. So I know how fast I know how fast this dot is moving to the right. Okay. Yeah, I would say that's kind of a general picture. Would you? Like this dot is moving. This radar station is fixed. This is fixed at 2. Right? I would say this is almost like my general picture right now. What would be the difference between that picture and the one at the instant in time?
Could we like put those together and kind of make a triangle?
Well, you may want to. You may want to. I'm not sure if we'll want a triangle or not yet. Let's.
Okay.
Yeah, I mean, we might need a triangle, but we want to have an appropriate motivation to draw a triangle if we're going to do it. So the only difference between the general picture and the exact instant in time picture is that here it says the plane is headed directly over a ground-based radar station. At the moment, the plane is 6 miles from the radar station. What does that mean in our picture? The moment this dot is 6 miles from this dot, right? That means this distance from here to here is 6 miles. That's the moment in time. Be careful, it's not saying the distance from the ground over is 6. It's not saying that, right? Distance from the plane to the radar station. Straight line distance.
So,
Okay.
Professor, quick question. If it were the distance on the ground, the problem would explicitly say it's the distance from the ground?
Yeah, it would have to say like, yeah, it'd be really difficult to even state it that way. You would have to say like the projection of the plane onto the ground, that distance is 6 or something like that. You would have to really be careful how you word it.
Okay.
But if it's just distance from the plane to the radar, that's it. I mean, it's almost like you're reaching out with a measuring tape, right? You're sitting here with a measuring tape trying to measure the distance between you and the plane. And you measure it out to be 6 miles.
Okay, got it.
Good. Okay, so you see how we have this labeled here, 6 miles, right here? That's not in our general picture, is it? We don't have that line drawn. So because it's not drawn, I'm going to draw it. And because it's not fixed, at 6 miles in my general picture, I'm going to give it a label. I'm going to label it H. I don't know why I picked H. Well, I kind of do. I kind of know why I picked H, because it's almost like a hypotenuse of a triangle that I'm about to draw. Right. So if I go like this and drop straight down, we know this side is 2, don't we? And that never changes in both pictures. That side's 2. Are y'all okay with this? All right. Let's try and write down what we're given and what we want. So we are given something here and we want something here. So someone tell me and I'll fill in. Either one, what you're given or what you want. Someone,
We're given
Austin, go ahead, Austin.
We're given the speed of the plane.
The speed of the plane, 600 miles per hour. I agree. What is that in terms of d something, d something?
So it's d something over dt.
Okay, so let me write that. Does everyone understand what's going on? Austin is saying that the speed of the plane is obviously the derivative of something, right? Because speeds are derivatives. And Austin's saying it's the derivative of something, not quite sure what it is yet, but it is with respect to time. And that should be your 600 miles over hours, right? Right, Austin?
Yes.
But Austin, you're not quite sure what this variable should be.
Yeah.
And you know why you're not sure? Because it's not in your picture. You have not assigned it. You have not assigned that a variable yet, right? It's the rate at which something is changing. What though? It's not the rate that H is changing, right?
Yeah, I
It's
guess.
not the rate that this is changing. It's the rate, some other variable. So this is kind of this is where, remember, Dilpreet, you were asking me earlier, is like the formula, like obvious. This is not obvious.
Is it the base of our triangle?
Okay, so you're talking about, is it this?
Yes.
Okay, well, let's just call that something. Can I call it X maybe? Is that okay? We'll just call that distance X. That would be the distance from the radar station all the way over to the bottom of this triangle, which is basically dropped straight down from the plane. If you call that X, right? If we call that X, and Austin just said, let's call this X, then is X changing at 600 miles an hour?
Yes.
Well, this point's moving, right? This point right here is moving to the right at 600 miles per hour, isn't it?
Yes, so X would be getting smaller.
So that's the same as this point, right? Like the shadow of this on the ground, that would be moving over this to the right also at 600 miles per hour, wouldn't it?
Yeah. So X wouldn't change, right?
X is changing. If this starts moving, right, then this triangle starts moving and that point starts moving, which means X starts moving.
But
It
isn't
starts getting
H
smaller.
is it? Maybe I'm thinking about it's like too much trigonometry, but if H is 6 and the height's 2, then you already have the answer for the third part.
That's right, but you're not allowed to look at the instant in time yet.
Okay.
You have to look at it in general. So look, I have an animation that might make this a little easier for us. There we go. So we've got this plane flying overhead, right? And right about, here, somewhere in here, when the distance between the two is 6, let me see, it's right around here. Oh, 5.99. So right at this instant, I want to know how fast that red line is shrinking, because it is shrinking, isn't it? Right now, at this point in time, it is shrinking. I want to know how fast it's shrinking. But I want you to pay attention to the dot moving across. The speed of the dot moving across the screen is also the same as the speed of this bottom corner of the triangle, right? They're both moving at the exact same speed. And so that's why if we label the bottom of this triangle X, then X is changing at 600 miles an hour also. Is that clear to everyone?
Yes.
Okay, but we have one more little thing we have to be careful with. In this picture, is X growing or shrinking? In the picture, the way we've drawn it,
Shrinking.
it's shrinking, right? Which means that dx dt, I'm going to write here, dx dt, since it's shrinking in our picture, I need to put negative 600 miles an hour. Because think about it like this. If you're standing at the radar station and you're measuring the distance between you and that dot on the ground, that thing is coming at you at 600 miles an hour, which means that distance is shrinking, getting smaller, right? So we have to use a negative value so that X shrinks instead of grows. Understand? All right, that's what we're given. Good job, Austin. Who wants to tell me what we want?
Can I go again?
Yeah, go ahead, Austin.
We want, it would be d of h over d of t.
DHDT. So what, Austin, you're saying, at the moment that we're 6 miles from the radar, the plane's 6 miles from the radar station, here's the key words. How fast is the distance between them changing? Well, the distance between them is h. And so we want to know the rate of change of h, which means we want to know DHDT at what moment in time, Austin?
At 6 miles from the
It's
radar.
what 6 miles?
Wait, can I say that again?
You said at 6 miles. I agree, but what at what quantity is 6 miles? Refer back to your picture. At the moment, the plane is 6 miles from the radar station. What variable is that in our picture?
6 miles, sorry. Right? No,
I didn't hear you. I'm sorry.
when h is 6 miles?
When h is 6 miles. Okay, it's very important that we don't just put at 6 miles, because are you talking about h or are you talking about x? We're talking about h, right? When h is 6 is when we're interested in. All right, I think we have everything. A general picture, we have an instant picture, we have what we're given, what we want, and at the moment we want it. So what comes next?
We have to do the implicit derivative of the given.
Of an equation, right? Of an equation. So we need the equation now. So let's see, I'm going to call on somebody. Carla, I think you already asked a question today,
Yes.
but I'm going to pick on you anyway. Okay, Carla, when you look at finding the equation to use, you always want to look at the variable here
Mhm.
and the variable here. And look at your general picture and come up with any equation you can come up with that relates X and H.
So the equation I'm thinking is like the Pythagorean theorem,
Yeah,
maybe?
exactly. We have a right triangle here, don't we?
Yes.
We have a right triangle. We have the equation a squared plus b squared is c squared.
Mhm.
Yeah, we can use that. As long as it connects X and H together and it's a legitimate equation, we can use it. So Dilpreet, do you see, Dilpreet, how it's not obvious? Like in the wording of the problem, it doesn't tell you to use a right triangle,
Yes, sir.
right? You have to extract that from the drawings. Okay, but good. Here's our equation. We have x squared plus,
It's like if you make one mistake and you're all ruined.
it's all over. Yeah. That's why related rates is not fun for most students. There's zero room for error and there's plenty of places to make mistakes. Okay, Carla, is that okay the way I wrote that?
Yes.
Now, does everyone see that I used 2 here? That because the plane was 2 miles high, I could leave that as 2, but I can't fix X and I can't fix H. I cannot fix those until after I take the derivative. So let me just clean this up. All right, Carla, we're going to keep going with you now.
Okay.
It's time for implicit. So we are going to do the derivative with respect to what, Carla?
Respect to time.
Time, and we're going to do it on the left side. And we're going to do the same thing on the right side. All All right, here we go. Carla, what do you got?
So for the left side, it's 2x times dx over dt. And then the 4 would just stay or would go to 0?
What do you think? Derivative of 4, derivative of a
0.
constant would be 0. Okay, so I can put here plus 0, I can just leave it out. What do you want me to do?
Just leave it out.
Leave it out? Okay, so that's the derivative left side. What about the right side?
So the right side would be 2h times dh over dt.
Perfect. That's perfect. Good job, Carla. You're off the hook. Does anybody have any questions over that? This is great. We have the equation that we have differentiated implicitly. Let's start taking a look at the things in this equation. Let's start with the things that are obvious. dx dt. Well, that's right there. I'm going to be able to replace that with negative 600. dh dt is what I want, and it appears right there. I'm very happy to see it because that's what I'm trying to solve for. I also have an h here, don't I? Do I know the h at the moment in time we're talking? Yes, at this instant, I know h is 6, so I've got h. The only thing I don't know here is the x. Do y'all see that? I don't know x at the moment in time. But can I get x?
Yes.
Yeah, because now you can look at the instant in time, and at that instant in time, here's what our triangle looks like.
Should be,
Right?
root
That's at the
32.
instant time. And we can use a Pythagorean to get x, can't we? So I'm just going to say x squared plus 4 equals 36. That's x squared plus 2 squared equals 6 squared. And x squared must be then 32. Subtract 4 on both sides. And then I take the square root and I get plus or minus square root of 32. And I'm going to use the plus because it's the length of this side of the triangle. So positive root 32. So now I have that piece also. I have x. Everything else is now just plug everything in. So let's see who's up. Let's see, Ryan. I've got Ryan here. Ryan, are you here? I see Ryan, but no response. Okay, how about Vivian?
Yes.
Okay, you're all you're going to do here is just plug in and tell me what to write down. So I'm going to rewrite this. You just tell me what to write.
Okay, it's gonna be 2 times the square root of 36.
32.
Oh, 32, sorry.
It's all right.
Times 600, negative 600
Negative 600.
equal 2 times 6 times, oh yeah, then dh over dt.
Yep, and that's what we're trying to solve for. So we'll just leave it like that. All right, good. I think at this point, we can just get a calculator out and figure out the left-hand side. So on the left side, I'm getting negative 6788.23 equals 12 times dh dt. And then just divide by 12. I get negative 565.69 is dh dt. So Vivian, you're still up here, okay?
Okay.
What are my units here, Vivian? What are the units for this number? So look at this and tell me the quantities they represent.
Okay. Wait, can I see the question?
Yeah. So you're looking for h and t. So up here, h is going to be
Height.
it's a distance, isn't it? I mean, it's like a length of something.
Yeah.
Right. And if h is the length, we're measuring our lengths in what here? What are our units? Miles, right? Okay, miles. And then what about our time measurement? What are we measuring our time in here? It's not super obvious, but look at the speed of the plane. Miles per hour, right? MPH, miles per hour. So our time measurement is hours and our distance measurement here is miles. So this answer should also be in miles per hour, right? So negative 565.69 miles per hour is dH/dt. So the rate, you're standing at the radar station. Plane is flying over 2 miles above you. It's traveling at 600 miles per hour. At the exact instant that the plane is 6 miles from you, the rate at which the distance between you and the plane is changing is negative 565.69 miles per hour at that instant in time.
Would the answer be the same if it was approaching from the other direction?
Well, what you could, yes, it would be, but think about this at this moment in time. Where is it? Right about here, right about there. It was about 6 miles right here. At that instant, the distance between you is changing at whatever answer we got. If the plane flies over you and then goes to the other side, now the plane's moving away from you, right? And so if this was 6 miles, it would be the answer we just got, but positive. So it would be like if the plane's now moving to the right and you had a rope, you were holding onto a rope that was tied to the plane, right? Then that rope would be coming out of your hand at 565.69 miles per hour. That's how fast the rope would be coming out of your hand. And then shortly thereafter, all your fingers would fall off from the rope burn. But that's how fast the rope would be coming out.
Thank you.
All right, what do you think? That was different, right? That was a different problem. Different
This
sorts of geometry.
Since the answer is negative, it just means that the distance is getting shorter, right?
Yeah, that means the distance between the two, the radar and the plane is closing, right? The distance is closing, getting smaller.
Okay.
All right, let's try another one.
I have a quick question on the last one.
Yeah.
I was able to follow along pretty well, except right there on the 36. Wasn't sure where you got the 36 from.
Here?
Yes, that one right there.
Using Pythagorean, a squared plus b squared equals c squared. So x squared plus 2 squared equals 6 times 6 is 36.
Oh, okay. I was just trying to like short brain it. I wasn't getting it.
Yeah, but you understand I'm using the Pythagorean, for a right triangle, a squared plus b squared is c squared.
Yes, I get it now.
Okay. All right, let's do another one. Was it 205? We're doing okay. I think what I'm going to do is I'm going to give you about 5 minutes to see if you can't come up with something here. Pictures and, see if you can't figure out how to get the pictures drawn and the variables, what you're given, what you want. This will give you some idea of how well you're adapting to this new idea here. All right, 5 minutes. Remember, your instant picture, you can fix everything in time, but your general picture, you can only fix the things that don't change. Like a 20-foot pole doesn't change, right? A 6-foot man doesn't change. Everything else is changing now. Give you about another 15 seconds. Okay. How about Gabriel? Gabriel? You there? How about Axel? Benjamin?
So I kind of thought about like a triangle with another triangle on the end of it, kind of.
Okay, so did you start out by, do you feel it? Maybe I can see your picture. Did you draw a picture?
I'm not quite the artist, but
It's okay. Can I see it?
it,
It won't show it because don't worry about it. Don't worry about it.
okay. Yeah.
It's okay. How about I'll draw it and you tell me if yours looks like this. So did you start
Okay.
with the ground?
Yeah, and
Okay.
the pole.
And a pole. So you just put a
Yeah.
pole here.
Yeah,
And
I
you
put
said
the light
that
on
pole
top.
is 20 feet tall.
Yep.
Okay. And then you put a man or something.
I labeled the bottom 12 feet, and then I put the man.
Okay, so you went from here to here. You labeled that 12 feet.
Mm-hmm.
And then you drew a man.
Yep, and labeled him 6 foot tall.
So I'm going to draw the man as another stick, okay? And that's 6
Okay.
feet.
And then,
Depending on your level of artistic ability, your man may look different.
And then to the right of the man, I put X.
Which was what? Where? On the ground?
On the ground, yeah.
And that's his shadow?
Yeah.
So how did you determine how far out to draw his shadow?
It's a variable. I'm not
Sure.
sure what it's going to be.
You're not sure exactly. You don't really know what that's going to be. I like the fact you called that X. Good. I'm okay with that. I like this.
I wasn't sure how to label the 7 feet a second, to be honest, but
okay.
That's
okay.
about where I'm at with it.
All right. So you said something about a triangle.
Yeah. So the top of the pole down to the top of the man, and then from the top of the man to an undisclosed length.
Shouldn't that be the tip of his shadow, though?
Yeah. So we don't know H or X.
So you called H what? The whole distance from here to here?
From the man to the ground.
You don't know what that is. Okay. I'm going to just stop you right here. This is really good. Okay. If you start to get something like this is good. One of the key aspects of this picture, though, is that the distance from the man to here, to the end of his shadow, should be where this line here comes down, hits the top of the man's head, and becomes his shadow on the ground. This is all his shadow, right? Everyone get that? Understand that? Is this picture the instant picture or the general picture right now, the way it's been drawn?
That would be the instant.
This is the instant in time. And the reason it's the instant in time is what?
The 12 feet.
The 12 feet has been locked, right? In reality, the man is moving, right? So that distance is not 12 while he's moving. It varies. So let's draw the picture below this of the general situation. We have the pole. We have the man, right? This time, the distance from here to here is not going to be 12. It's going to be something else, right? Because it's changing. And we can't call it X because Benjamin's already told us that the distance from here to here, right, which is his shadow, has already been called X. So we better call it something else. What do you want to call it?
D.
What, V?
No, D.
D,
Delta.
okay. I would avoid D, and here's why I avoid D. It's the only letter you should avoid, because when you do the derivative with respect to D over T, it just looks weird. dt. You can use D, but then you might think that that D is a derivative again.
Can we do
So-
Y?
Use L.
You could use L. And it doesn't matter what you use, okay? You want to go with L?
Yeah.
Can I use capital L?
Sure.
I don't like lowercase l because it can look like a 1 unless you do it in cursive, but I'm not doing anything else in cursive. So I'm going to go with capital L.
Okay.
So if I were doing this problem myself, I would have called this M for the man, and I would have called this S for the shadow. But that's just in hindsight now, right? That might be the way you'd want to label it, but it doesn't matter. And then this right here, I'm going to just label it because that does factor in somehow into the problem. This is our general picture. Are we good? Maybe we can start putting down what we're given and what we want. Okay, maybe we can start. So when you're doing these problems, it's never step 1 followed by step 2 followed by step 3. It's the pictures and what you're given and what you want, and you just kind of work them all out as your brain is processing all the information. So you might do a little bit of this, then come back here and say, oh, I need to add this, or, oh, you know what I'm saying? It's not one step that has to be followed in steps that have to be followed in order. Okay.
So
Somebody
what
give me
does-
something here.
I'm
What?
sorry.
Huh?
What does that where does that 7 feet go?
Yeah, good question.
Is that a distance from pole to, I mean, that, no, that can't be this.
Look what it is. It's the speed. It's a speed of 7 feet per second, right? Speed is a derivative. It's the speed of what, Dilpreet? What's moving at 7 feet per second?
Man.
The man, right? The man is moving at 7 feet per second. Which variable here represents the man? X is his shadow, right?
Yeah.
L is the distance from the man to the pole. So if the man is moving to the right, right? If the man is moving to the right at 7 feet per second, then shouldn't L be growing at 7 feet per second?
Right.
Right? That's the rate that L grows. So this should be dl dt is 7 feet per second. What are we trying to find? This is a tough one. This is tricky. You have to be careful here.
Trying to find dx dt.
How fast?
Oh wait, no, dx plus.
Shadow.
How fast is his shadow moving along the ground, right? But relative to the pole. Well, unfortunately, in the way we drew our picture, we don't have a distance that represents that. That would be this distance from here to here. That distance. We want to know how fast that distance is growing. And since we haven't labeled it, I'm going to call it capital T for like total, the total distance, okay?
Can we make like 2 triangles? Like one from the pole to L and then have another triangle from the pole to, I mean, from the man to X?
Well,
And put them
you're
together.
asking if we can create 2 triangles,
Yeah.
right? We can, but my question to you would be, why are you doing that right
Because I want to know the whole thing at the bottom, I guess. I don't know.
now? We have to get to the point where we're actually interested in drawing triangles. I don't know if I'm going to need to draw a triangle or not yet, right? I'm just trying to figure out what I'm given and what I want. And then after I figure that out, then I'm going to find the equation that relates the 2 quantities together, right?
Okay.
And if it winds up that I need triangles, I need triangles. But I'm not going to just start drawing triangles just arbitrarily out of nowhere yet.
Okay.
I just want to make sure we're following like mentally a process. That's all.
Okay, then yeah, because my head's like, okay, we're connecting this and this, and I'm looking for this, and then it's all I'm like, okay, that's a triangle, that's a triangle when I draw it. So then I might end up needing to use triangles. So then why don't I try this? And that's what
And we are going to need them. We are going to need them. I just want to make sure that the motivation for using them is well founded. All right.
okay then, because that's just what my brain's automatically thinking as soon as we draw the picture. So I need to slow my roll pretty much.
You don't want to get ahead of yourself because you have to know what you're looking for, right? You have to know what you're looking for. We want dt, 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 dt. When do we want it? Okay, at what moment in time?
For the for the instant.
Yeah, what's the instant? There's some information about the instant that we can put here.
When L is equal 12?
When L is 12. Good. I don't know who said that. When L is 12 feet. Was that Carla? Who was that?
Yes, sir.
It was good. Okay, good. So when L is 12, because it says when he is 12 feet from the pole. Well, 12 feet from the pole is the measurement from here to here, but that's what L is, right? All right, I think we have what we need to start asking the question about the equation. We need to somehow relate capital L to capital T.
Would be L plus X equals T, something like that.
L plus X is T. You all agree with that? I'm so glad you saw that. Okay. Do you all agree with this? L plus X equals T. Is that true?
It should be.
Yes.
Okay. Is that an equation that puts L and T together?
Yes.
Yeah.
Could we differentiate that with respect to time?
Yes.
Yes, right? We could. All right. So you might think this is going to work. Let's see why it's not. Okay. Let's just do the work. Right now, this is our equation. We think, okay, this is going to work. Let's take the derivative with respect to time on the left and the derivative with respect to time on the right. Okay, what would the derivative on the left be? Well, just do them individually, right? So dl dt plus what?
D
of X over D of
X
T.
dt equals d capital T dt. Y'all agree with that? Now, are we happy to see this? Let's see. D capital T with respect to T. Yeah, do we have that there? We have it right here, right? Good. Happy to see that. dl dt, do we have that? Yeah, I'm happy to see that. Here's where we run into the problem. dx dt. Do you know what dx dt is? You do not know what dx dt is.
No, it's the third variable.
It's another variable that we have it in our picture, but we have no idea how fast x is growing, do we? We know how fast the man is moving, but we don't know how fast his shadow is growing, which means we're not going to be able to do it. We can't do this. We have too many variables in here. We need just L and just T. Questions? We're stuck right now a little bit. Let me go back up to the general picture. We still need to find an equation. I'm going to label this 20 because that was 20. I'm going to label this 6. So if we look at this from a slightly different perspective, we have what Danielle was referring to here. We have a right triangle inside of another right triangle like this, where from here to here is L and from here to here is X, right?
Yes.
And then this entire side is T. And we also know that L plus X is T. We know that because, well, if you add these two up, you should get T. All right, now what we're going to do is we're going to split this into 2 triangles. We're going to have a big triangle And we're gonna have a small triangle. The big triangle is this one. Okay, and the small triangle is that one. And so we can label these sides 20, T, and I'll call this H. And well, let me call this capital H. Call it capital H because it's bigger than the other one. This one will be 6. And then what goes here?
X.
X, and I'll call this a little h.
Aw.
All right. Now, why have I drawn 2 triangles? Because we're about to use a property of triangles that if you have 2 triangles that have the same angles, so this angle and this angle have to be the same, don't they? Because this angle forms this for the big one and the small one, right? They both have to have this angle the same. They both have this 90-degree angle the same, which means that these angles have to be the same.
So it's side angle side.
You're thinking, I think you're thinking pre-cal, side angle side, how we solve for triangles.
Yeah.
Yeah. All I'm saying here is that these triangles are what we call similar triangles.
Aha, remember that. Yeah.
So these triangles are called similar, meaning that they have equal angles. Now they're not the same size, but they have equal angles. And anytime you have 2 similar triangles, you have to know this. Okay, this is from pre-cal. You have to know that anytime you're working with similar triangles, the ratio of corresponding sides must be equal. What? What that means is that if you take this side and divide it by this side, it must be equal to the corresponding side 6 over this corresponding side X. So for similar triangles, the ratio of corresponding sides are congruent. That's something from pre-cal. So here's another way you could have done it. That's one way we could do it. Another way we could do it is this. We could have taken the 20 and divided it by the 6. And that should be the same as taking the T and dividing it by this X. Or you could do the X divided by the T must be equal to the 6 divided by the 20. As long as they're corresponding, then you can set up the ratios. So there's several different ratios we could set up. I have set up this black one first. 20 over T equals 6 over X. Now what I've done is I've created a relationship between T and X, haven't I? What are we trying to get a relationship between? T and L, right? Between T and L. Right now I have a relationship between T and X. Let's work with this relationship. Do you all agree that this is 20X equals 6T? Yeah?
Yes.
Okay, so I have an equation that relates T and X together, but I want it to relate T and L together. But what is X? Go back up to this equation right here. What is X? Could we solve for X here?
Yeah, X
It
is
would be T minus L, wouldn't it?
Yeah.
So why don't I replace this X with T minus L? Now, why am I doing that? Why am I replacing that X with T minus L? What did I just create?
create an equation that relates L and T.
That's an equation that has T and L in it only, right? And now I have a relationship between T and L, and X is no longer there. And this is great because now I can distribute the 20 through. And let me bring my T's to one side. I subtract 6T on both sides. And I move the 20L to the other side. That looks like a pretty good equation, doesn't it? It's an equation that relates T and L together.
It looks cute. Yeah.
Yeah, it's very simple, isn't it? It's a very simple relationship. So once I have an equation, can't I just differentiate that with respect to time? Right, so this is our equation right here. And so if I take the derivative with respect to t on the left, and the derivative with respect to t on the right, I will get 14 dt dt equals 20 dl dt. Because it was 14 in front of t, I just bring the 14 for the ride, take derivative of t. Because it's 20 in front of L, I bring 20 for the ride, take derivative of L with respect to t. And now I should be able to do this because I know dl dt, right, is 7, and dt dt is what I want. So now I can start plugging in. I'll do this in red. So dt dt is what I want to know. dl dt was 7. Wait, no, was it? Yeah, it was 7. So if I take this answer 20 times 7 and divide it by 14, I'll have my answer. Oh, 10. Duh. 10. 10 what?
Feet per second.
Feet per second is dt dt. Okay, I think we should back up and just recap. Started with the problem, tried to draw a picture. We got an instant and a general picture. We labeled L and X, but then we wound up realizing we really wanted to know how fast T was changing. We tried to come up with a relationship between T and L. The first relationship we had, even though it was good, we didn't know what dx dt is, so we couldn't work with this. We realized we had two triangles. We could split them up. We realized those are similar triangles, which means we could set up a ratio. Once we had the ratio, we had an equation. We replace X with what X was. Then we differentiate that with respect to T, and we plug things in and we get an answer. This is the way it is. Okay, this is the way these problems are. Every problem is going to be uniquely different. The geometry of each problem is going to be uniquely different. So, yeah.
So I'm a little lost on what happened to L equals 12 feet.
L equals what?
12 feet.
I'm so glad you asked that. I was going to not mention it because I just felt like maybe it would be pushing too far. Was that Natalie that asked the question?
Yes, sir.
Natalie is asking a very good question. Once we took the derivative here, right? Here was our derivative. All we had to do, sorry, not that one. This is our derivative. And we were interested in finding this, right? Do you all see that to find dt dt, the only thing you need to know is dl dt? And that nowhere in here did we actually ever have to plug in the L as 12, right? The L equals 12 had no impact at all on the rate of change of T. And that's what Natalie was asking. Why didn't we use L as 12? We never used it. We didn't. And what that tells you is this: the speed of the shadow, okay? The speed of the shadow only depends on the speed of the person. It does not depend on how far the person is away from the pole, which leads to a very, very counterintuitive thought here. I don't know if this makes sense to you, but what we're saying is if a person is walking away from a pole at a certain speed, their shadow, the speed of their shadow has nothing to do with how far away they are from the pole. It only has to do with how fast they're moving. So if you were to go back to this picture, I never showed you the picture of the person walking here.
So they
Okay.
just only gave us to confuse us.
No, it's part of the information, but it's not relevant to the answer. So if you were, this person's walking away from the pole at 7 feet per second, and this shadow is moving away from the pole at 10 feet per second. And it doesn't matter where he is. He can be here, that shadow is moving at 10 feet per second. Go over here, shadow's still moving at 10 feet per second. Go here, shadow's still moving at 10 feet per second, regardless of where he is. Natalie, does that answer your question?
Yes, sir.
In the previous problems we did, the instant time did matter. This problem, it doesn't. Okay, we have 4 minutes. I want us to at least look at the next problem. A conical cup is 4 inches tall and 6 inches wide. Well, you know what? Let's not look at this. Let's talk about the review. You have a test a week from today, right? And I put a review out there for everyone. Let me get it real quick. I should have emailed it to you, yes?
Yes, got it in this inbox.
There it is.
Business.
Okay, so here's the review. And for the first, what, 6, 7, for the first 7 problems, I asked you for the raw derivative. And I mentioned that once in class. The raw derivative means take the derivative, show me you know how to use the rules. Don't worry about cleaning it up algebraically. Okay, so you don't have to simplify the answer. And I'm doing that on the test because I don't want you to waste time doing algebra. I just want you to show me you know how the rules work. Now, when you look at these problems, they go in the order in which we learned them. Okay, so we have power rule, product rule, quotient rule, and then we get chain rule. So the rest from 4 down is all chain. And then we get to 8. 8, we start doing implicit differentiation, implicit differentiation, implicit differentiation, but we're asking for a second derivative. So I did one of those last class. Then a problem where you're supposed to find the equation of a tangent line, which means you have to use the formula y minus y1 equals m times x minus x1, but you've got to figure out what the slope is. So to do the slope, you have to take derivative of this, but you have to use implicit differentiation to do that. So just going to let you do this, okay, and figure out how, you know, you're going to work through this, see how it goes. And then on number 12, this is the way I did it in the tests that I've given in the past. I usually give the students like 3 different related rate problems. The first one is the more difficult one. The second one is easier. The third one is the easiest of these 3. I let the student choose one of them, but they have different point values. So in other words, if you choose to do the harder one, you can get more points. If you choose to do the easy one, then, well, of course, it's going to be easier to do, but you can't get as many points. So basically, if you do the easy problem, then let's say that this test was worth 100 points. If you do the easiest problem, then like the highest you could get on the test would be a 95. Because it's not worth as many points as something like this. And I have 2 of those. Oh, where's the other one? I thought there was another one. Oh, next page. No? I thought there were 2 sets of word problems. Are there not?
No, you just scrolled by it.
It's just one?
No, you have right there.
Oh, there it is. I went by. Okay, so there, and then I don't get this. Why is this not?
You're scrolling by it, like
I'm scrolling by it. So there's number 12.
12 and 13.
Yeah, where's 13? Okay, there we go. There's 13. It wasn't showing it. There we go. There's 12. So there's 3 problems to choose from, right? And then 13 is another 3. So I told you last class that I would keep it to the easier problems on the test, right? And I think I'm going to still do that, but I'm going to offer harder problems for more points, so you can get, you know, higher grade. See how it goes, okay?
So if we only did 2 of the easier problems, we wouldn't get any additional points. They wouldn't add together. We just
I
get.
think on this test, I told you that the problems would be easier. So I think the way I would work it is if you did the easy one here and you did the easy one on the next one, you could get 100 on the test. But if you did B and A, then you could get like a bonus higher than 100. Because I did tell you I would not put hard problems on this test since we're not going to have enough time to do some of the harder problems. We still have more problems to do. Okay, so next class, when we come back on what, Tuesday, right? I'm going to do more related rate problems, some of the harder ones.
Like the cone.
The cone and then,
And that chick running around in circles.
yeah. Someone running around a track and trying to figure out how.
And her friends watching her like a creeper, like in the stands.
Yeah, exactly. Okay, everyone, we good?
Yep.
I said I'm not going to do a review. I'm not going to do the solutions to this, right? That
So
was
we
the
can
deal.
come to your
I give
office
you
hours?
review. I don't give you solutions.
So can we
But-
come to the office hours on Monday?
If you come to my office hours, I will be happy to go through some problems with you. But first thing I'll do is ask you, like, what did you do? Like, I want to see what you did. I don't want to just be like, okay, you didn't, you walk in and say, I didn't do anything. I want you to at least have tried it. Okay. If you need to get in touch with me this weekend, then you can text me. Call me if I'm around, near the computer. I'll be happy to join and help you out if need be. Have a good weekend, everyone.
Have a good weekend.
Thank you.
Bye. Bye.
Best of luck to you.
Bye. Have a good weekend.
Professor.
Yes.